So now this video discusses about what we call as the extreme values of a function. So what are the extreme values of a function and the principles behind? If we say extreme values of a function, these are the highest values or the highest value or the smallest value or the smallest values in which the function attained within the given interval. So that's what we call them as extreme values. These are the highest values or the highest value or the lowest value or the lowest values in which the function attained within the given interval. That's what you call them as the extreme values. This is a typical application of the differentiation. Whatever the principles that will be used will be the principles of the differentiation. So make sure you understand the principles should be the techniques of the differentiation, and rather should be the differentiation rules and the techniques, because we can just have to use the principles in the video. So you just have to familiarize yourselves with the product rule of differentiation, the quotient rule of differentiation, and some other actually differentiation techniques that we talked about. And also some techniques on how we can be able to solve some actually equations, either the quadratic equations and the cubic equations. We should also have to understand about solving some equations that involves the and some other equations that involves the fraction parts and also even the negative parts. So this video, we just have to have the typical applications of the differentiation. So make sure you have the good background on the differentiation stuffs, because we just have to apply in the video. So keep that in mind. Let's say we have, this is a two-dimensional Cartesian plane. Let's say this is the case. Let's say this is a typical two-dimensional Cartesian plane. And assuming that we have a curve, assuming that we have a curve of a function. Let's say this is a typical curve. I should have this. Let's say this is a curve of a function, and which is going over like this. Let's say this is a curve of a function. You just have to extend this to this point, and I should have somewhat. Let's say I should have this. Let's say that is the case, and let's say this is the curve of a function f of x is equal to y, and let's consider that as that. And now let's pay attention on the points, on the turning points that the graph is possessing. And let's say we have, this is the point, and say the x value corresponding to that point, it is given as c1. And we also have, should be also this point. That's, I'd say, should be this point as well. That is a typical turning point, although it is incomplete. But let's say I should have mainly this. The x value corresponding to this point, I should have it as, let's say, c2. And now for this point, I should have it as c1. I may say x1, x2, whatever, but for the sake of interest, I just have to use that as c1, c2, and sort of. And also we have this point. Let's say that is the case, and the x point, actually x value corresponding to that point, it is given as c3. And I will also have this point, and the x value corresponding to that point, I should have it as, let's say, somewhere about c4. And I also have this point, and whose x value are quite as c5. And also we have, let's say, let me just have to put this one as this. Let's say I should just have to lower the curve, should be somewhere like that. For the sake of interest, I just have to lower that one as this. But in a given case, you can have the curve of different nature, but let me just have to hand that on as that. Let's say this is the point, and the whose x value is given as, let's say, c actually 6. And now there is something you have to understand. So we are saying extreme values. So should be extreme values. These are the highest values, or the highest value, and also the lowest values, or the lowest value in which the graph do attain in a given interval. And let's say that's to have C1, let's say given as A, and let's say C6, I should have it as, let's say, should be B. And now this corresponds to have it as interval in which the graph runs. So the graph runs from A to B. So we should have that. So which means, to make it more clear, then I should have this is a C1. Let's say this is a C1. Just have to make it more clear. This is now C1. It means this will be given as, should be C2. And I should call this is a C3. If I'm to be much or more realistic, then I should have that as that. And this should be given as C4. Let's consider the case being given as this. And now the graph runs from A to B. So within the case, let's consider the points, or the turning points associated with a curve. As you can see, what is the overall highest point on a curve? The overall highest point on a curve, it is given as this point. And now this point, it is known as the absolute maximum point. So it is said to be the absolute maximum point. Let me just have to note this is, let's say, let's say this is a point A, this is a point B, C, D, E, let's say F. So actually in that case, a point D, it is known as the absolute maximum point. So it should be the absolute maximum point. So it should be maximum point. That is the highest point overall, and it is also known as the global. It is also known as the global maximum point, absolute maximum point. So it should be absolute maximum point. That is a point D. That is the point which is the highest overall. And what is the point which is the lowest point overall? And now the lowest point overall, it is given as, should be point E. And therefore a point E, it is known as the absolute minimum. The one which is the lowest of all. That is absolute minimum point. And that should be a point E. As you can see there. That is the point which is over a minimum point. So in extreme values, we have two types of the extreme values you have to understand. We have what you call as the absolute maximum. We have what you call as the absolute maximum, and we have what you call as the absolute minimum. And now the y value corresponding to the absolute maximum point, it is known as the absolute maximum value. So the y value corresponding to the absolute maximum point, it is known as the absolute maximum value. So this is how I can have it. Let's say we should have that as that. So if that is the case, let me say it in this way. Now the x should be the y value corresponding to the absolute maximum point. Let's say it is given as y1, and therefore this value is known as the absolute maximum value. That is the the largest value overall. And the y value corresponding to the absolute minimum value should be the y value corresponding to the absolute a minimum point, it is known as, should be the absolute minimum value. Let's say it's given as should be y2. So we should have that. So the highest point overall, it is given as a point D, and it is known as the absolute maximum point, and the y value there it is known as the absolute maximum value. And the lowest point overall, it is given as absolute minimum point, and the y value there it is known as that of the actually absolute minimum value. So that's how we start that understand. And from that point, we start to understand about what we call as the local maximum point and local minimum point. And now, upon ignoring the highest points, and that is a point D and a point E. And now let's consider the other remaining points. So on the other remaining points, which one is a point which is largest of all? On the other remaining points, if we consider a point A, point B, point C, as well as the point F. So which point is a largest overall if we consider the remaining points? You know, the highest point overall for the remaining points, it is given as a point F. And therefore, a point F, it is known as the local maximum point. So a point F, it is known as the local maximum point. Local maximum point. And that's point F. And which point is lowest over all? It means if this is the local maximum point, it means the least of the remaining points within, they are known as local minimum points. So should be the local minimum points. Should be that local minimum points. And thus we have a point A, we have point B, we have point C. So these points are said to be the local minimum points. These are the points that are lower than F, and within the case where we have already highlighted the absolute maximum and absolute minimum point. So it should be that. And now the y values corresponding to the y value corresponding to the local maximum point, it is known as local maximum value. So in this case, this actually y value here, it is known as local maximum value, and the y values corresponding to the other actually local minimum points, that are known as local actually minimum values. So we should have that understand. So in other ways, absolute maximum point, that is the point that outshines overall. And the y value at that point, it is known as absolute maximum value. And the absolute minimum value, that is also the point that shines over but below the rest. And the y value there, it is known as actually absolute minimum value. Otherwise, the other remaining points, what it does is that we have either the local max and also the local minimum. So in the sense that on the other remaining points, the point which outshines the rest, it is known as the local maximum point. And the y value there, it is known as that of the local maximum value. Otherwise, the least remaining points are known as local minimum points, and the y values are said to be the local minimum values. So that's how we start that understand. And now let's say we have the following cases and see how we can be able to identify the local maximum point and the local minimum point, and also that of the absolute maximum as well as the absolute minimum. Let's say we have, this is a typical Cartesian plane. Let's say that is the case, and thus let's say we have a graph of a function, and which is given us, let's say that is the case. Let's say that is the graph of a function f of x is equal to y, and let's say this is a point A, and let's say this is a point B, this is a point C, this is a point, let's say, should be D. Let's say this is a point D, and let's say this is a point E, and say we should have that should be let me just have to use this. Now on this graph, which point is absolute maximum? Absolute maximum point. So which point is that? Actually, you know, as you can see here, the point which is outshining the list, it is given as the point D, and therefore that is a point D. And which point is absolute minimum? The one which is the lowest of all, it is given as should be a point E. So that is the absolute minimum point. That is a point E. And now we should have to consider the least points, and which point is said to be the local maximum point. Now the point which is the local maximum point is given as the point B. That is a local maximum point. So it should be local maximum point, and that's point B. And how about the local minimum point? You know, the local minimum point, it is given as that of the point, should be point C. So that's how we should have it. And how about, let's say this is case. This is a case. Let's say we have, this is a case that we have it as this. And let's say this is the graph of a function. Let's say it should be given as this is a typical curve. Let's say that is the case, and let me have this one. Let's say this is a typical case. Should be that. Let's say it is a function, it is a graph of a function f of x is equal to y. So what can you say about the local maximum, local mean, absolute, as well as the other case? You know, this graph, as you can see it here, it means it can keep on going up to the post infinity, and it can also keep on going up to the negative infinity. And therefore this graph is only having what equates as the absolute minimum point, which is this point. So the graph is only having the absolute minimum point. So it should be that that is the only lowest point overall. You start it as that. And how about, let's say this is a case that we have. Let's say we have it as this. And now we have, this is where the graph is ending. And let's say it is a closed point. And we have it as that. Now what can you say about the actually a local max, local mean, absolute value for that case? You know, this is the only point which is lowest overall, and therefore that is absolute. That's absolute minimum point, which is this. And now this is the only point which is highest, and therefore it is known as the absolute, should be absolute maximum point. We should have it as that. And how about, let's say this is a case that we have. Let's say we have the case of this graph. So what can you say? Let's say we have, this is a typical graph, and say this is open point, and this should also be given as the open point. So as you can see, the graph has no maximum, the graph has no local max, even the local mean, and also has no absolute max as well as the absolute mean, because the end point, it is open point. That means it is undefined, and also this point, it is open because, and hence it is undefined. Hence the graph has no absolute max as well as the absolute mean. So just keep that in mind. And how about, let's say this is a given case. So what can you say about this point? Let's say this is a typical graph. We should have it as this. And now we have the end, which is should be the crossed circle, and this is, let's say, also the crossed circle. Let's consider the case being given as that. And now for this case, this is only the highest point, and therefore that is absolute maximum point, and this is the only lowest point, therefore that is absolute minimum point we should have. And what if, let's say, we have a case like this, and appreciate, and say we have this is a case. Let's say we have a graph that goes like this, and it goes like that, and it goes like this. So what can you say about this graph? Now we have this point, this point, this point, this point, this point, as well as this point. Now for this case, what it does that the only highest point is given as this point, and the only and thus the actually absolute maximum point, and this is the only lowest point, therefore that is absolute minimum point. And now on the remaining points, this is the highest point, that is local max, and this is the lowest point, that is said to be the local minimum point. We just have to keep that in mind. And how about, let's say we have a case like this. Let's say this is the graph of a function. It should be the graph lands like this, and it goes like this, and it goes like this. Let's say it is a graph of a function f of x is equal to y. And the graph starts from here, and it goes like this point, this point, this point, as well as this point. Now this point is said to be the absolute maximum, and this is absolute minimum, and this is local max, and this is the local minimum point we have. So I understand by now you know what is graphical aspects of the extreme values. That's a local maximum point and local minimum point that you have, and that of the absolute as well as the minimum. And also try to appreciate this, and let's say the graph goes like this, and it goes like this, and the graph goes like this. And now for this case, this is the only highest point, and that is local actual absolute maximum point, and this is the lowest point, that is absolute minimum, and these points. Now what can you say about these points? So I want to see the responses in the comment section below, and thus you should have it. And now let's have to discuss about what declared as the critical should be the Fermat's theorem and the critical values. Fermat's theorem and that of the critical values. So what is Fermat's theorem is all about? And now let's consider we have a curve with a function. Let's say we have this is a two-dimensional Cartesian plane. We should have to use the same principle. Should be talking about, and we'll be singing about the two-dimensional Cartesian plane, and let's say that is y-axis and this is x-axis, as you already know about that. We have this, that is should be x-axis, and let's say we have a curve with a function, and that goes like this. Let's say this is a curve with a function. In that case, let's say that is a typical problem that you can have. Let's have this. Of course, should be given as that. And now let's consider the points should be the turning points of the graph. You know, assuming that the graph is starting, let's say, assuming that the graph is starting from the x value, should be the graph is starting from this point. And what is the x value? I should declare as a. And the graph is ending at this point. And what is the x value? I should declare as b. So now, which means the graph, has lines within the interval a to b. Should be that. Let's say the graph, it is a graph of a function f of x, which is equal to y. And now let's consider the turning points. So for this case, we have this point, and let's say I should have it as should be c1. The x value corresponding to that point, I should have it as c1. And this is should be c2. That is the point, and this is the point. I should have it as, let's say, c3. And I should have, let's say, this is the point, should be c4, and this is the point. Of which we understand that according to the principles behind, based on what we have discussed recently, let's say this is should be, let's say this is a point A. Let me just have this. Let's say this is a point A. This is a point B, C, D, E. Let's have the point F. Let's consider the case being given as that. And on this point D, it is known as the absolute maximum point. So a D is known as the absolute maximum point. And the point should be a point A. It is known as the absolute minimum point. And now, on the same case, the point B, it is known as the local maximum point. And that of the point C, it is known as the local minimum point. And now the point of interest is, what you have to understand is that the x value corresponding to these points are known as the critical values. So the x value corresponding to those points of interest are known as the critical values. So which means the x value here, which is given as a, it is also said to be the critical value, and this is the critical value, critical value, critical value, and this is also critical value. We start that. And now, how can you be able to determine the x values corresponding to these points? So how can you have the x value c1? In other words, how can you have the critical value c1, critical value c2, critical value c3, critical value c4? And now those values are calculated using what they call as the Fermat's theorem. And what is the principle behind the Fermat's theorem? There is something you have to understand about this. If you look at those points, those points contains the horizontal tangent lines. If you look at a point B, we can be able to come up with the horizontal tangent line at the point B. It should be given as this. In other words, those are the points with the horizontal tangent lines. We can have it as that. And on the same case, at the point B, actually at the point D, we can also be able to have the horizontal tangent line, and that goes like that. And also at the point D, actually C, you can also have the horizontal tangent line that goes like that. And also at the point E, you can also be able to have the horizontal tangent line, and that goes like that. So you start to understand that, in whichever the case, horizontal actually a tangent line is said to be having the gradient being given as L. So in all cases, horizontal actually a straight line, its gradient is given as L. And Fermat's theorem, it is based on this aspect. So how should you have those critical values if that is the case? And now from the fact that these points are having the horizontal tangent lines, then this is how the Fermat's theorem has to be. In order to calculate the critical values corresponding to these points, and according to the principles behind the Fermat's theorem, it states that the first derivative of a function should be equated to 0, and we'll start to solve for x. And now if this is the case, we're saying the x values in these points are the same as the critical values. Therefore, f of c prime is equal to 0. And this is what equates as the Fermat's theorem. So which means the first thing we should have the first derivative of the function, and from there we should have to express the x. Actually, we should have to express the x in terms of should be c. Then we should be able to solve for c. And those values that are going to obtain as the value of c are said to be the critical values. So we should have that understand. And now let's appreciate the following questions. Another question says that we should have the critical values, and we should also have that, and just have to simply we should have the critical values. So find the critical values for the following actual functions. Let's say we have a function f of x is equal should be x squared and minus, let's say 6x plus sum about 7. You know, in order to have the critical values, we should use the Fermat's theorem, which is this, that the f of c prime is equal to 0, and therefore we should have to have the first derivative, which is given as 2x minus 6. Then now for this case we should have it as f of c prime, and now we should have to have it as f of c prime is equal to 2c minus 6, and we should have to equate to 0, and therefore we should have to solve for c, and which is equal to 0, we'll have it as 2c is equal to 6, and x is equal should be a 3. So should be we should have to solve for c, not x as such. And that is therefore the critical value is given as, you know, that of 3. That is the critical value. Or else you may think of having it in this format. And that is first thing we should have the first derivative, and that is given as 2x minus 6. And now from there we should have to equate the first derivative equal to 0, and that is 2x minus 6 is equal to 0. And now for this case x is equal to 3, and therefore we should have to conclude that as the critical value is given as 3. You can also have it in the same way, like that. And what if, let's say, this is a given case that we have? Should be, let's say, have a function f of x is equal to, let's say, x and times 4 minus x into the power sum of the power 3. So how do you think we should have the critical values corresponding to this? You know, first thing we should have the first derivative, and for that case f of x prime is equal, so which differentiation should be, it should be applied at this point. Now overall differentiation should be given as the product law, and thus we should have it as u prime v plus v prime u. And what is the u? We should have it as x. And what is the u prime? We should have it as 1. And therefore v is given as 4 minus x to the power 3. And now the derivative of v will be given is actually will be done using the chain rule of differentiation. And now what it does is that the v prime is given as 3 times, you know, the inner function to the power 2 times the derivative of the inner function, and which is given as the negative 1. And thus we should have it as negative 3 and times 4 minus x squared. We should have it as that. And now we should have to substitute, which is given as f of x prime is equal to, now what is u prime? That is given as 1, and times what is v? That is 4 minus x to the power 3, and the plus what is v prime? That should be given as, should be negative 3 x minus, should be 4 minus x rather. So should be that of 4 minus x to the power, thus should be, by the way, we're saying v prime to the power 2 and times u, which is given as x outside. Of course this is the same as having it as, should be f of x prime, and being given as, so should have it as 4 minus x over the power 3, and this x times negative 3, that is negative 3x, and times 4 minus x to the power 2. And now from there we should have to equate that onto 0. and so for x. And thus we should have it as f of x prime is equal to 0. That is Fermat's theorem. And therefore have it as 4 minus x to the power should be 3 and the minus 3x and 4 minus x to the power 2 is equal to 0. And how do you think we should have this? Then as you can see, we can be able to factor out 4 minus x to the power 2. That is the common factor. So have it as 4 minus x to the power 2, and that is we are having it as somewhat about should be 4 minus x and thus minus 3x and should be equal to 0, as you can see there. And using the zero product theorem, what it does is that we should have it as 4 minus x to the power 2 is equal to 0. And now for this case, we should have to introduce a square both sides. That should be given as 4 minus x is equal to 0. And therefore, x is given as 4. That is the first actually critical value. And therefore, the critical value is given as should be 4. And we should use the other case here. And how do you think we should have it? So which means we have it as 4 minus x minus 3x is equal to 0. And thus we should have to have the like term, so have it as negative 4x is equal to negative 4. And thus x is equal should be 1. And therefore that is also a critical value, which is given as 1. So these are the critical values of the function. So how do you think, let's say we have this case. Let's say this is a typical function, and which is given as, let's say, f of x is equal to, let's say, x squared over should be x minus 2. So how do you think we should have the critical values for this case? Principle remains the same. Using the Fermat's theorem, f of x prime is equal to 0. Then we should have the derivative. And what is the differentiation which we have to use? We use what we call as the quotient of differentiation. And that is u prime v minus should be v prime u. And divided by v prime. So in this case, our v has to be the denominator, and thus v is given as x minus 2, and what is the v prime? We have it as 1, and which means u is given as x squared and the u prime is given as 2x. Now we just have to simply substitute x prime, f of x prime is equal, what is the u prime? That is should be that of 2x, so have it as 2x here. In times, what is that of should be v, which is given as should be x minus 2 and minus. So what is v prime? That is should be 1 in times what is that of u? We have it as x squared and divided by, so that's we should have it as x minus 2 to the power 2. By the way, we should have power 2 here. And therefore, f of x prime is equal to, we should have it as 2x squared and minus should be 4x, and thus minus x squared divided by somewhat about x minus 2 to the power 2. And that's how we should have it. From that point, we should have something about f of x prime being given as, now the like terms we can have it as x squared and minus 4x, and thus divided by should be x minus 2 to the power 2, and that should be that. And now from there we should have to equate this to 0, according to the Fermat's theorem. X squared minus 4x, and that's divided by x minus 2, and thus about the power 2 is equal to 0. And at this point, we should not have to have the cross multiplication. Therefore, we should have to solve, on the numerator as well as the denominator separately. So have x squared minus 4x is equal to 0. And we should have to factor out x minus 4 and is equal to 0. And therefore, the critical values are given as x is 0 and x is equal to should be 4. And we should also have to do the same on the should be that of the numerator. Denominator rather will have it as x minus 2 to the power 2 is equal to 0, and we still have to introduce a square both sides. And what it does is that we have x minus 2 is equal to 0, and therefore x is equal to 2. And the critical values are given as, C0, and that's 2, and that's 4. So that's the basic idea behind that one. Now, how do you think we should have this? Let's say if we have a function f of x, and that should be given as, let's say, square of should be 2x and minus, let's say, x squared. So how do you think we should have the critical values associated with this one? Principle remains the same. What it does is that we should have the first derivative. That will be done using the chain of differentiation. So that is the same as having it as to the power half here. And thus we should have it as the half and 2x minus x squared into the power negative half. And times the derivative of the inner function, which is 2 minus 2x, like that. And now from that point it means we should have the product of the half and this. And that we should have, something about, should be a 2 minus a 2x and divided by 2 and times 1 over using the laws of indices. Thus we should have it as 2x minus x squared in the square root, which is the same as we can have it as, we can think of factoring out 2, and simply we can have it as 1 minus x and divide by square root of 2x minus x squared. I think should be that. That should be f of x prime. And from that point, what it does is that we should have to apply the Fermat's theorem and have the critical values. And that should be given as 1 minus x divided by the square root of, should be 2x. Should be 2x and minus that of x squared is equal to 0. And we should also use the same principle where we should have to solve, for the numerator, we should have to solve the numerator as well as the denominator separately and have the critical values there. Let's see how we can have it. We should have it as 1 minus x is equal to 0, and x is equal should be a positive 1. And the square root of 2x minus x squared is equal to 0. We should have to introduce a square both sides to remove the square root. Have it as 2x minus x squared is equal to 0. We should have to factor out. We'll have it as x2 minus x is equal to 0, and therefore x is equal to 0, and x is equal should be somewhat about 2, and therefore the critical values are given as, a 1, 2 as well as 0. So that's how you can have it. What if, let's say, this is a typical case that we have? And imagine we have a case like this. Let's say if we have a function f of x is equal to, let's say, x minus 3x to the power, let's say, 2 over 3. So how do you think we should have the critical values associated with this function? Principle remains the same. We should have the first derivative. That will be given as 1, and that's minus should be 3 times 2 over 3, and x to the power 2 over 3 minus 1. And what would be that 2 over 3 minus 1? Using that of the butterfly method, we'll have it as 2 minus, and it should be, let me just have this. So it should be, what is the common denominator? That is 3, and 1 to 3, that is 3, and that should be given as 3 here. And that is 2, we can have it as negative 1 over 3. So that is the power here. And what will go up next? As you can see there, we'll have it as f of x prime. We'll have it as 1 minus, this will cancel, have it as 2x to the power negative 1 over 3. of which we have to equate this to 0. We have it as 1 minus 2x, 2x to the power negative 1 over 3 should be 3, and which is equal to 0. And now from there we have to transfer this to the other side. What you can have is should be negative 2x to the power negative 1 over 3, and which is equal to negative 1. And thus we should have it as x to the power negative 1 over 3 and is equal to half. And from there, how should we have to have that out? Using the laws of indices, what it does is that this is the same as having it as 1 over x to the power 1 over 3, which is the same as 1 over 2. And thus we have to think of cross multiplying. We'll have it as 2 is equal to x to the power 1 over 3. And we should have to express this in terms of the cube root, and for you to have the should be the good picture of this. This is the same as having it as the cube root of x is equal to, and now we should have to eliminate the cube root to have it as, we should have to introduce a cube both sides to have it as x is equal, and this is 8. So this is the critical value of the function. And what if, let's say, this is a typical case? Let's say we have a function f of x is equal, let's say, x squared in times should be x to the power 2 over 3 rather in times, let's say, x squared minus should be 4. So how do you think we should have to calculate the critical values associated with the function? Principle means the same. We should have the first derivative. In now this case, we should have to use the product of differentiation. That is given as u prime v plus v prime times u. And what is the u? We have it as x to the power 2 over 3. And what is the u prime? We should have it as 2 over 3. And x to the power 2 over 3 and minus 1. Thus we should have it as 2 over 3 minus 1. And what would be that? That is 3, 2. Should be negative 1 over 3. So we should have it as that. So negative 1 over 3, of which the u prime will be given as 2 over 3 and x to the power negative 1 over 3. That you can have it as 2 over 3 times the cube root of x. You can have it as that. Times the cube root of x. You can have it as that. That is the u prime. And now what is the v? It means the v is the other thing, which is x squared minus 4. And the v prime is given as 2x. And we have to simply substitute into the function. And what it does is that the f of x prime will now be given as, what is the u prime? That is should be 2 over 3 times the cube root of x. And times what is a v? We have it as x squared minus 4, like that. And plus, what is v prime? We have it as 2x. And what is the u? That is given as x to the power 2 over 3. We have it as that. And now from that point, we should have to be minded that, f of x prime will now be given as, should be 2 times the x squared minus 4 and divide by, and that should be 3 times the cube root of, should be x, and plus, so we should have to have it as 2 times x to the power 1 plus 2 over 3, using the laws of indices. Since this x is having power 1 in same basis, we should have to add the powers, and thus now we should have it as 1 plus 1, should be 2 over 3, 2 over 3, that should be given as 3 here, and that's 2, 3, that's 5 over 3. So it should be 5 over 3. And that should be that. And therefore, f of x prime will not be given as, it should be 2x squared and the minus 8 divided by 3 and times the cube root of x. And that's plus 2 times the x to the power 5 over 3. So that's how we have it as that. And now from that point we have to apply the Fermat's theorem, and which is that we have it as 2x squared minus x divided by 3 times the cube root of x and minus 2x, the power 5 over 3 is equal to 0. And how do you think we have this one up next? We have to express this as the single fraction. And what it entails is that, we should have what is the common denominator. Let me have this one here. So what is the common denominator? We should have, somewhat about 3 times the cube root of x. And now 1 into this is the same thing. Therefore, we have to multiply this and that. But let me give you what will happen here. Of course, 2 times 3, that is the same as 6. So we should have it as 6 here. But what will happen for these two? So using the laws of indices, what it does is that we have it as x to the power 5 over 3 and plus 1 over 3, because this cube root of x, that is the same as x to the power 1 over 3. So we have to add this. That should be given as, should be x to the power 6 over 3, which is the same as x to the power 2. So we have it as x to the power 2 here. That's what will happen. And now from there, this is 1, and 1 times this will be the same as, should be 2x squared and minus 8, like that, and which is equal to 0. And at this point, we have to solve for the numerator as well as the denominator separately. So which means we have it as 3 times the cube root of x is equal to 0. And thus we should have to divide everything by 3. And we should have it as the cube root of x is equal to 0. Then we should have to introduce cube both sides. Both sides will have it as x is equal to 0. So that is the first critical value that we have obtained. And from there we have to make use of the numerator. And how do you think we have it there? Now we have it as 2x squared, and by the way, common, it should be those are the right terms. We can have it as, should be negative 4x squared and minus 8 is equal to 0. You should have to bring 8 to the other side to have it as negative 4x squared is equal to 8. Then x squared should be negative 4, should be that of, we have, then we should have, should be x squared is equal to negative 2. And there's no square root of negative 2, and therefore this one has no little solution. So the only critical value is given as should be c is equal to 0. That is the solution. So some questions might be too involved, but we just have to use the same principles, and the way we solve the equations, it is the same way we should have to apply those things. So now let's consider this kind of equation. Let's say I have a equation f of x is equal to, let's say, should be x to the power negative 2 and times ln x. So we should have the critical values for this function. So how do you think we should have it? Principally means the same. We should have the first derivative of the function, and thus we should have to use the product of differentiation. That will have it as u prime v plus v prime u. And what is the u? We have it as x to the power negative 2. And the u prime should be given as negative 2x to the power negative 3. We'll have it as that. And the v has to be given as ln x. So the v has to be given as ln x. Thus we should have, and what is the v prime? We'll have it as 1 over x. And f of x prime will be given as, what is the u prime? That is a negative 2x cubed, and times what is v? That is ln x, and times should be v prime, that is 1 over x, and times what is u? We have it as x to the power negative 2. So thus we have it as, it should be negative 2x cubed and linear x. And this we have it as, plus x to the power negative 2 over x. So we start to apply the laws of indices there. What it does is that this is the same as having it as x. And by the way, having that one, but let me just have to apply the same way there. That is the same as having it as x to the power negative 2 and minus 1, which is the same as x to the power negative 3. It is the same as that. So what it does is that we have it as negative 2x to the power 3 linear x and plus x to the power negative 3. Or else you may think of having this, if you may wish to. Then what we have it here, that is the same as having that and as should be, that is the same as having that and as 1 over x times 1 over x to the power 2, and which is the same as 1 over x cubed. And using the laws of indices, this is the same as x to the power negative 3. So that is the same as that, in case you may wish to. But whichever the way, much as it is acceptable, then you're okay to learn that one up. So which means we have it as this, and from there we have to apply the Fermat's theorem there, and such that we should have it as negative 2x cubed and linear x plus should be x to the power negative 3 is equal to 0. That's what you have it as that. And we should have it as somewhat about, for this case, what it does is that we should have to express this one as a fraction, or have it as negative 2x cubed times linear x and plus 1 over x cubed is equal to 0. We should have to express this as the single fraction. Now what it does is that we should have it as x cubed as the common denominator, which is equal to 0, and that's 1, and we have x cubed in times negative 2x cubed times linear x. That's what we should have it at that one. By the way, we should have this is plus 1 here and times linear x, so we should have to distribute cube there. And what we have it should be negative 2x to the power 6 and linear x, and that's plus 1 over x cubed and is equal to 0. So we should have to solve the numerator as well as the denominator separately, and thus we have it as x cubed is equal to 0, and therefore we should have to introduce the cube root, and thus x is equal to 0. That is the first critical value, and we should do the same with the numerator here. So what would be that? We have it as negative 2x to the power 6 linear x plus 1 is equal to 0. And how do you think we should have this? And what it does is that we have it as should be negative 2x to the power 6 linear x plus 1 is equal to 0. And now we should have to make it okay to solve for actually x here. So I'm leaving this actual task for you and try to go over that. How do you think we should have that one? So try to express that one. And now let's see how we can be able to have the absolute maximum and the absolute minimum values of the given functions in the intervals below. Let's say I have a function f of x is equal, let's say 12 and plus that of 4x and minus, let's say x squared, in the given interval given us should be 0 to 5. So how do you think we should have the absolute maximum as well as the absolute minimum value for this function? First thing we should have to apply the Fermat's theorem. We should have the key values, it should be critical values. That will be given as 4 minus 2x. And f of x prime is equal to 0. That's 4 minus 2x is equal to 0. And now that's x is given as 2. And therefore, the critical values are given as 2 and including the values in interval. We call them as endpoints. So endpoints has to also be included as the part of the critical values, and thus we should have it as 0 and 5. Now, before we conclude that 2 is part of the critical value, we should have to test, is 2 found within the given interval? Exactly, it is yes, actually, because 2 is found between 0 to 5. So actually 2 is really a critical value. Then we have to substitute these values into the original function. So we should have, first of all, f of, let's say, 0, which is this, but you may start with whichever the value. What is f of 0? We'll have it as 12. And we should have f of 2. And what would be the f of 2? Now we should have, this is should be 12, and this is plus should be 8, and minus should be 4, because if we substitute x, okay, this x for 2, we'll have it as 4. That should be that. And what is this? That is should be 4, then we should have it as 16. Should be 16, and then we should have f of 5. What would be that? And I should also do the same. That is 12, and plus should be 20, and minus 25. That should have it as, should be, somewhat about, so we should have it as, should be 12 plus 20 and minus 25. So what would be that? That is 7. Now on these actually x values, or the critical values, which critical value has given us the highest value of y, and that is the 16. Therefore the absolute maximum value it is given us is 16, and the absolute point, actually absolute, it should be the absolute maximum value is given as, should be 16, and the absolute maximum point it is given as 2,16. This is the x value, this is the y value. But now for this case, this is absolute maximum value, and what is the lowest value, which is given as 7. Therefore this is absolute minimum value. So that's how we conclude it in that way. So that's how we have to understand how we can be able to conclude that in that way. And what if, let's say, this is the case, f of x is given as, let's say, should be 2x cubed, and say minus 3x squared, and minus 12x, and plus 1 in the interval given as should be negative 2,3. So how do you think we should have the absolute value, absolute maximum, as well as the absolute mean? Principle remains the same. We should have the first derivative, which is given as 6x squared, and minus 6x minus 12. Then we should have to equate this to 0, and thus we should have that as should be a 6x to the power 2 minus 6x minus 12 is equal to 0. We can think of simplifying this, since we have the common factor, which is 6. So have x squared minus x and minus 2, which is equal to 0. Then we start to solve for x. Should we use the factor method? Will it work? Yes, it will work. We'll have it as x squared and minus, should be plus x minus 2x minus 2 is equal to 0. And thus we have it as x plus 1, and negative 2 x plus 1 is equal to 0. And therefore we have it as x plus 1 times x minus 2 is equal to 0. And now for this case, the critical values are given as x is equal to negative 1, x positive 2, and including the endpoints, that is x is equal to negative 2 and x is equal to positive 3. These are the critical values. And now from there, we have to learn the same principle. We have to substitute, the critical values into the original function, and we have to determine which one is giving us, the absolute maximum and that of the absolute minimum. So it should be that. So it's to have f of negative 1. What would be that into the original function? So that is negative 2 and negative 3, positive 12 plus 1. So it's to have it as, what is that? That is negative 5, negative 5, and plus 13. And what would be that? That is given as, should be somewhere about 8. So f of 2, that will be given as, and this is 8. 8 times 2, that is 16. Should be 16. And this is should be 12 minus 12. And this is negative 24 and plus 1. So what you should have to understand is should be 16 minus 12. Should be 16 minus 12 and minus 24 and that of the plus 1. So what would be that? That is given as negative 19. And we should have f of negative 2. What would be that? And that is given as, it should be negative 16, and it should be negative 12, positive 24, and plus 1. And what would be that? Now we have negative 16 and negative 12 plus 24 and plus 1. And what would be that? That is given as negative 3. And we should have f of 3. That would be given as, 27 times 2. So 2 times 27, which is given as 54. And we should have, this is should be that of 9 times 3, that is 27 minus 27. And this is should be 12 times 3. And that should be given as 36. So minus 36 and plus 1. So we should have to understand that we'll have 54 minus 27 and minus 36 plus 1. That should be given as negative 8. So which one is giving us the highest value? So that is 8. So this is the absolute maximum value. And the lowest is given as negative 19. Therefore, that is the absolute minimum value. So that's the basic idea behind that one. But in terms of the point, it means the point negative 1, 8, that is absolute maximum point, and this is 2, negative 19, that is absolute minimum point. But in terms of the value, it is given as the y value. What if, let's say, we have this kind of a case? Let's say we have a function f of x, which is equal to, should be the ln of x squared, let's say plus x, and plus 1. In the interval given us should be a negative 1, 1. So how do you think we should have this? In all approaches, in the previous example, I did not check whether the critical values I got from the calculations were within the interval that we had, but just have to check through. So if it happens that whichever the critical value is not within the given interval, then we should have to eliminate that one. We should have to ignore that one. Don't make use of that one. So let's apply the same principles here. So we should have the first derivative. That should be given as, 1 over x squared plus x plus 1, and times the derivative of inner function, which is given as 2x and plus 1, which is the same as 2x plus 1 over x squared plus x plus 1. That should be given as that. So that is the first derivative. And now from there, we have to equate that onto cell. What it tells is that we have it as, should be 2x plus 1 divided by x squared plus x plus 1 is equal to 0. And we should have to solve for this separately and have the critical values. So which means we should have it as 2x plus 1 is equal to 0, and therefore x is given as negative half. And you should also have x squared plus x plus 1 is equal to 0. And how do you think you should have this? Let's think of using the quadratic formula. And what it does is that, but let me just have to use let me just have to check if it is having the real solutions or not using the discriminant. So a is giving us 1, b is giving us 1, and c is giving us 1, and the discriminant is giving us, b squared, that is 1, and minus 4ac, that's 4 times a times c, which is the same as 4. And now since the discriminant is giving us negative, actually a negative number, it means that one has no real solution. It cannot be solved. Therefore, the only critical value from the calculations is given as negative half. And really, it is it within the given interval? Yes, negative half, it's within the interval. So which means we have the critical values given as negative half, negative 1, as well as the positive 1. Then we have to substitute and check. And that's, f of 1, what is that? We have it as ln, that is 1, 1, and that is 2, it should be ln 3. And the f of should be a negative 1. What it does is that we have it as, this is a positive 1, negative 1, that should be 0, and this one corresponds to have it as ln 1, which is the same as 0. And what is f of should be negative half, and also do the same and check which one is the best. So try to get that now. And also try to have this at your own time. Let's say you have a function f of x is equal, let's say x minus should be the cube root of x, and within the interval given us negative 1 comma positive 4, and try to have this at your own time. You should have the absolute maximum as well as the minimum. And f of x, let's say, is given as should be x times e to the power negative, should be the power x over 2, rather x to the power x over 2, and in the interval negative 3 comma 1, that's a closed interval rather. And also have the same case in this. Let's say we should have f of x is equal to e to the power x divided by that of 1 plus x squared, and that's within the interval 0, 3. We should have that one. And now let's finally appreciate how we can have the critical, should be the local maximum as well as the local minimum. So how do you think we should have the local max as well as the local minimum? We should have the local maximum as well as the local minimum values of the functions. Now, on the case of the local max as well as the local min, no interval of the function is given. Now for this case, let's say if we have a function f of x is equal to, let's say, x squared and minus 6x, and let's say plus 7. So how do you think we should have the local max as well as the local mean for this case? Principle remains the same. We should have the first derivative, which is 2x and minus 6, and we should have to get that to 0. That's simply we should have x being given as, now x will be given as, it should be 2, and this is the critical value, and from there we should have to substitute that one into the original function. Have it as f of 2 is given as, this is 4 and minus 12 plus 7, and what's that? That is negative 8 plus 7, and which is given as, should be a negative 1, and this is either the local max or local mean based on the nature of the actual graph. So for this case, the graph, since this is a positive, it means the graph will have to concave upwards. It means the graph will have to concave upwards because this is a, but if you may think of having sketched the graph, it will really tell whether this is either local max or local min, since we only have that particular as a single value. So it should be that. And what if, let's say, this is a typical case? Let's say we have it as f of x we have f of x, and which is given us is 6x squared and minus x cubed. So how do you think we should have it? We'll have the first derivative being given us, it should be 12x, and minus should be 3x squared. And now from there we should have to solve for the critical values, and thus we should have to, we can think of simplifying, and since we have the common factor which is 3, this is 4x minus should be x squared is equal to 0. We'll factor out x, we'll have it as is equal to 0, x is equal to 0, and x is equal should be 4. And now these are the critical values, and from there we start to substitute into the original function. And now using the same principle, have it as f of 0 is equal, that is also 0, and f of 4 is given us, and this is should be 16 times 6. What would be that? 16 times 6 is given as 96. 96 minus, what is 4 to the power 3? Should be 4 to the power 3. Rather should be 4 to the power 3. That should be given as 64. So minus 64. So what do you think we should have it as? 32. And now this is the highest value. Therefore, this is a local maximum point. It should be, this is the local maximum value, and this is the local minimum value, like that. And what if, let's say, this is a typical case that we have? Let's say we have a function f of x is equal to x cubed, and that should be 3x squared, and the minus 24x, and should be plus 7. So try to have this one, and also at your own time try to have the local max as well as the local mean for the following cases. And that is, let's say f of x is equal should be x minus 1 to the power 2 and times x minus 3 to the power sum 2. So try to have that one in that way. And also try to understand something about, let's say, if we can have this kind of a case. Let's say the function f of x is equal 3x cubed and minus 2x squared plus 7x plus 1. So try to have that one. So that's how we start to understand the principles behind the actually extreme values. So thank you.